The probe lands on Titan and touches a liquid methane shoreline. It looks like water, it moves like water, then it breaks. The surface ripples under its weight, slow waves spreading outward as if this place can hold it, as if this is a landing that worked. For a second, everything looks normal, calm, stable, safe enough to continue. Then the shell snaps. Hairline cracks race across its outer skin. The metal tightens, then splits. Systems spike, then vanish. It should be floating. It should be stable, but it is not. The cold hits first. Not a breeze, not a chill. A crushing drop to nearly 300 degrees below zero, cold so absolute that every exposed part contracts at once, faster than it can survive. The surface looks soft. The reaction is violent. If it is liquid, it should cushion the landing, but it does not. The outer layer fractures again, deeper now, pieces separating as the structure loses its shape. Signals fire out, then stop. Power stutters, then dies. It cannot hold. The shoreline keeps moving, slow and silent, while the system inside begins to fail piece by piece. No explosion, no warning, just a quiet collapse that no one can reach in time. The mission does not fade. It cuts. It was built to land. It was built to survive contact. But the moment it touches, the environment rewrites the rules. And everything we send here breaks before it can even begin. Methane rain falls on Titan. The probe is already damaged, and now the sky joins in. Droplets hit the surface like ordinary rain, tapping the ground, gathering into thin streams, then pulling themselves into dark rivers that slide around the landing site. It looks familiar. It looks survivable. Then the parts stop moving. A hinge tries to turn, but catches halfway. A wheel locks in place. A seal that was meant to stay tight begins to shrink, harden, and pull away from the frame. The failure spreads. This is no longer one broken shell on one shoreline. From above, the storm can stretch wider than 1,000 miles, pouring the same liquid across plains, channels, and low ground no machine can escape once it starts. The environment keeps changing. Materials built for extreme cold should stay predictable. If they survive the temperature, they should keep their shape and keep doing their job. But they do not. They change under contact. A part that should flex becomes stiff. A joint that should slide begins to grind. A seal that should protect the inside becomes the opening that lets the outside in. Control is slipping. The probe can be designed for cold. It can be sealed against liquid. It can be tested for pressure, impact, and darkness. But Titan is not attacking one piece at a time. It rewrites everything at once. The rain keeps falling. The rivers keep forming. The systems keep seizing. Nothing stops it. Even if we adapt to the cold, the environment changes the behavior of the materials themselves. The machine is still there, but it no longer moves like a machine we control. Scientists build Titan inside a chamber. Then the materials go in. A strip of metal lowers into liquid methane, clean and steady, while the glass fogs and the temperature drops into a range where normal behavior stops meaning much. At first, this looks like progress. The failure has a shape now. Cold is the enemy.
Far from the sun,
A sample bends under a test arm, then snaps instead of flexing. A rubber seal that should stretch turns hard at the edge. A coating meant to protect the surface flakes off in small, bright pieces. Now the damage makes sense. If extreme cold is the cause, then stronger materials should survive it. But they do not. Inside the chamber, the reaction slows until the material almost seems frozen in time. On Titan, chemistry can move up to 1,000 times slower than it does on Earth. So every repair, every battery response, every protective layer starts losing the speed it needs to save the machine. The system looks explainable. The probe broke because the cold made solid things brittle. The seals failed because the liquid attacked them while the temperature stripped away their flexibility. The moving parts seized because the materials stopped acting like the materials we tested on Earth. It feels solvable. Build tougher parts, choose better seals, make the frame stronger. If the problem is just cold, then the answer is better armor. That is the trap. Titan conditions give us a clean explanation, and for a moment, control feels possible again. But that explanation depends on one dangerous belief. The environment is following rules we can design around. The sensors inside the Titan chamber start showing damage before the surface changes. The material looks untouched. Methane presses against it, soaking into edges that still look clean, sliding into gaps too small for a camera to catch. The sample sits there, smooth and solid, while the readings begin to drift away from what the eye can see. No crack appears. That is the failure. A seal holds its shape, then its strength drops. A coating stays flat, then its inside layers begin to separate. A connector looks locked in place, but the structure beneath it has already been altered. The warning disappears. If the outside looks intact, the inside should still be protected. But it is not. Titan does not have to smash the machine open. Its atmosphere is 4 times denser than Earth's, pressing and carrying methane into places the design treats as safe. The environment moves through the machine before the machine can show it is dying. Control is slipping again. A part can pass the cold test. It can survive the bend test. It can come out looking clean enough to trust. Then it fails later, with no visible wound, no clear pattern, and no moment where anyone can say, "This is where it broke." That breaks the explanation. The problem was not just cold metal snapping. It was methane penetrating, absorbing, changing the structure from the inside while the surface kept lying. Nothing looks broken. Then the system stops. And once failure hides inside the material, we cannot predict it, cannot see it, and cannot stop it before Titan rewrites the rules again. Mission concepts fail before they ever reach Titan. The simulation will not stabilize. A redesigned lander appears on screen. Stronger frame, better seals, tougher moving parts, and every system is supposed to survive what destroyed the first design. Then the model runs. The joints seize, the seals leak, the power drops out. The failure is bigger now. It is no longer one material cracking, or one chamber reading drifting, or one hidden weakness spreading under a clean surface. Entire mission plans collapse on the table before anything is even launched. If better design is the answer, the new system should last longer, but it does not. Titan's methane cycle stretches across more than 3,200 miles, from clouds to rain, from rivers to lakes, from surface back into sky. A machine does not face one hazard there. It enters a moving world that keeps changing the test while the test is running. There is no safe setting. A wheel designed for the ground meets liquid. A seal designed for liquid meets pressure. A battery designed for cold meets chemistry that moves too slowly to recover in time. Each fix finds another rule. Control slips out of the design itself. We can make a stronger shell. We can choose better parts. We can simulate the cold, the liquid, the pressure, and the rain. But the whole system still belongs to Titan before it belongs to us. That is the collapse. Exploration needs time. It needs motion. It needs a machine that can keep working long enough to look around. Titan does not give it that long. The environment keeps rewriting the rules. And anything we send there enters a world we cannot fully predict, cannot fully control, and cannot make Earth physics fit.